engineering major.
My name is Sharvari. I'm a biomedical engineer.
Hi, my name is Athalye Dahlgren, and I am majoring in biomedical engineering.
I'm Geoffrey Scriver. I'm one of the interventional radiologists at UPM Medical Center. So I use ultrasound to place needles into patients to do various things, and these ladies have built this Phantom to allow me to train new interventional radiologists in the techniques that I do.
My name is Rachael Oldinski, and I'm an associate professor in the mechanical engineering department. I am the faculty advisor for the SEED project, the Abdomen Phantom. It's going to be a simulation tool for medical students and residents. Instead of having to use cadavers, which doesn't represent the lifelike mechanical properties of real human tissue, these students and residents will be using a biomimetic material that resembles real human tissue. It will be able to move, it will feel, it will have water, and most importantly, they will be able to image it through ultrasound.
The significance of our simulation is being able to allow medical residents and fellows to gain more confidence and practice in performing liver biopsy procedures with a simulation that is more realistic to that of a human before moving on to a real patient.
In order to produce a successful product, the following client requirements were met. The first requirement was that the model be biomimetic. This means that our simulation accurately represents the function and structure of the biological abdomen. Additionally, it displays proper echogenicity under ultrasound and provides accurate breathing motion as well. Next was replication. The model is easy to replicate using common household equipment. It not only remains inexpensive to produce, but also has parts that can be recycled and reused. And the last requirement was that the model come with a tissue library that displays the specific properties of varying concentrations of hydrogels.
Final design relied heavily on the use of polyvinyl alcohol, or PVA. PVA was used to create the liver, kidneys, skin, muscle, and tissue surrounding these organs. We used silicone molds of the liver and kidneys and filled them with PVA at different concentrations to create the correct shape of the liver and kidneys. To the liver, we added small balloon sacs filled with ultrasound fluid to act as abscesses. We also used thin latex balloons filled with water to act as the blood vessels. We oriented the balloons in a branching structure so that they appeared as branching blood vessels under ultrasound. After completing freezing and thawing cycles on these molds, the organs were then compiled into an organ box. The organ box was then placed inside of a moving box, which was inside of a large stationary box. The moving box is allowed to move back and forth because it is on drawer slides and it is attached to a linear actuator that is programmed to move a certain distance. 3D printed plastic ribs are attached to the stationary outside box and are placed over the organ box. A layer of skin made from PVA is then placed over the ribs. The simulation is then able to move back and forth through the use of an Arduino board and a linear actuator. The user is then able to turn on the simulation and start interacting with the model. After presenting the final design to the clients, they concluded that the simulation moved an appropriate amount as a humans would. They were able to complete multiple procedures such as liver biopsy, bile duct drainages, and abscess removals. They also concluded that the echogenicity of the liver, kidneys, abscesses, and vasculature was correct.
Initially, we had the idea that we played around with was using pluronics for the blood vessels, as well as using liquid nitrogen for the abscesses. And the problem was that it was just like overcomplicating the solution, and we were able to make suitable abscesses and blood vessels just using balloons. But the trade-off with that was that we don't have reusable blood vessels and we don't have reusable abscesses. Another trade-off that we had to make was rather than having only the liver move, we have to have the entire organ box move. So the kidneys are also involved in the motion, which isn't super biomimetic, but that just works for us right now because the kidneys aren't a very important part of the simulation.
Some technical methods, skills, and analyses we used to complete our final project consisted of soldering, coding, 3D modeling using SolidWorks and AutoCAD, use of the rheometer located in Dr. Oldinski's laboratory to test the hydrogel shear moduli, and qualitative analyses using the ultrasound machine lent to us through our clients. Compared to current simulations on the market today, our Phantom Abdomen was built at a fraction of the cost, while also providing more realistic qualities competitors did not include, such as a breathing mechanism. The social impact of our simulation lies in training sessions that will be held throughout the year in which a simulation will be used as a learning tool for medical residents and fellows to gain practice in performing liver biopsy procedure. What's next for our project is handing off our finished product to our clients, that being the drawer box assembly and organ box, as well as the technical documentation package, user manual, and our final design report.
I definitely think we succeeded. We were able to fulfill 100% of our client specifications, and we presented the model to them over and over again, and they were able to perform all of the procedures that they said they needed to. So I think that counts as success in our opinions, and I really can't wait to see what this project will be over time, the future iterations of our project, and we're very proud of what we've made.